Hi everybody, welcome back. Today we're going to have part 2 of instrumentation and controls in the liquefied natural gas industry. We have a lot to cover, so let's get started. In previous videos we discussed instrumentation, basic control loops, PID variables, and parameters. Today we'll review a few of those concepts, but then dig a little deeper to the control loops and control loop architecture specific to the liquefied natural gas industry. First of all, let's review a few of the fundamental control loop architectures. Open loop control. This is the simplest form of control where the control action is independent of the process. An example would be a timer-based schedule for a specific operation without feedback from the process. Due to the need for high precision and safety, true open-loop control is rare in critical LNG processes, but may be used for less critical auxiliary systems. Some examples would be a simple timer-based system. A central heating boiler controlled solely by a timer, where heat is applied for a fixed duration regardless of the building's temperature, is a basic example of open-loop control. Certain types of LNG vaporizers, particularly those used in pilot programs or specific applications, might operate on an open-loop principle. This could involve a preset flow rate of heating medium without real-time feedback on the vaporization process. Open-loop control might also be used in initial stages of cool-down. Cool-down involves cooling down the cargo tanks and associated piping to cryogenic temperatures around negative 162 Celsius or negative 260 Fahrenheit to prevent thermal shock and ensure the safe handling of the extremely cold LNG. Initial stages might involve a predetermined sequence of valve adjustments without continuous feedback on the exact temperature profile. While more sophisticated control is needed later, the initial phase can be open loop. Feed bypass valves. In some LNG plants, a feed bypass valve might be used to relieve pressure or manage flow in certain situations. While advanced control process systems might aim to minimize its use, there can be cases where it operates in an open loop manner to prevent issues like flooding or low temperature limits on chillers. Open loop control, it's a simpler design and it's usually a lower cost, but without feedback, it always has the potential for inaccuracy. So let's look at closed loop feedback. This is the most common type of control loop in the LNG industry. The controller compares a process variable like temperature, pressure, flow to a desired set point, and generates an output to a final control element like a valve or a compressor to bring the process variable back to the set point. A classic example is a programmable logic controller maintaining the flow rate in a pipeline. Cascade control. This advanced strategy uses two controllers, a primary and a secondary, to provide more precise control. The output of the primary controller determines the set point for the secondary controller. This is particularly effective for processes with multiple lags or disturbances. For instance, the main cryogenic heat exchanger. A primary temperature controller can set the set point for a secondary refrigerant flow controller. This allows the inner loop to quickly correct for disturbances in the refrigerant supply pressure before they significantly impact the overall process temperature. Ratio control. This type of control is used to maintain a specific ratio between two process variables. In the following example, there are two types of process variables. First is the output flow rate may change due to demand of liquid from the tank, and the second is variations in the input flow rate. The variations in the input flow rate happen due to changes in supply pressure. This causes variations in the tank level. The ratio calculation occurs outside of each loop to maintain the correct blend. And finally, feed-forward control. Feed-forward control loop is a control system that anticipates and compensates for disturbances before they can significantly affect a process variable. Unlike feedback control, which reacts to errors after they occur, feed-forward control aims to be proactive by measuring disturbances and adjusting the system to counteract their effects before they cause a deviation from the desired set point. In this example, disturbances will occur in the process flow. The feed-forward controller sends its control variable to the comparator. The process temp also goes to the comparator. The comparator PLC plugs these two values into an algorithm model and then adjusts the steam flow before the disturbances can affect the process temperature. And that's all the time we have for this subject today. Thanks for watching. We'll see you next time.